For part 3, let's look at a second common method of finding an approximate solution or a sequence of better and better approximate solutions to an equation of the form f of x equals y, and that's iteration towards a fixed point. This requires that you've seen things like the idea of a fixed point and iteration. But if you have seen that, you maybe know a little bit about how cool it is. So what we've got is a function f from, I was going to say Rn to Rn, but as usual, it doesn't need to define out all of Rn, from U to Rn. In this case, it's really important that not only ends are equal, but these really are the same space. So sometimes even if the ends are equal, we want to think of f as something goes from one space to a space of some different kind of quantity, maybe with different units, just happens to be the same dimension. Here, we really want f to go from Rn to itself. So, because that's the only way we're going to make this make sense with a fixed point. And we'll see how that fits into the proof of the inverse function theorem later. So here's the trick. We would like to create some new function, phi sub y. We fix a y as usual. And we would like to create a new function, phi sub y, from u to Rn as well, so that when f of x equals y, which is what we want to show happens, we want to find the x, that's the same, it's going to happen exactly when phi y has x as a fixed point. And it turns out that fixed points they have some very powerful methods and theorems associated to them. Okay, so we want to figure out, let me go to my cheat sheet here. We want to figure out when that's going to happen. All right, so I'm just going to put everything on one side. So we want phi of y of x minus x to be 0 at the same time that y minus f of x equals 0. Well, the easiest way to do that is to make these two left-hand sides equal. I'm not saying that's forced on us, but it's the easiest thing to do, and we're creating phi sub y, so why not? Okay, so in other words, we're going to say phi sub y of x, so I'm going to identify these two left-hand sides, just move it over, x minus f of x plus y. That will definitely show up again later, because in our the main version I'm going to show about the proof of the inverse function theorem, I'm going to use this method. Okay. Now, I am not saying this is always going to work. Okay, because what do we really need to activate the really good theorems about fixed points? We need phi sub y to be a contraction mapping. Okay, so that's an important thing you need to know about as a prerequisite here. Another way to phrase that is it satisfies what's called a Lipschitz condition, with the Lipschitz constant being strictly less than 1. So Lipschitz is going to be another thing, although I'll redefine that later on. But it's got to be a contraction mapping. And let me just remind you what that means. It means that the magnitude of phi sub y of x minus phi sub y of x prime, say, has got to be less than or equal to c. So if you look at the distance between the inputs, the distance between the outputs has to be less than or equal to some constant times that, where c is strictly less than 1. So it shrinks the difference between inputs compared to the outputs. And we have this wonderful theorem that says that iterating, and I'll give you the more precise version later, we're still just motivating stuff, iterating phi y, given this assumption, will drive toward a fixed point, and pretty efficiently if c is fairly small, if it's bounded well away from 1. Fixed point of phi y. Okay, so that means that you start with any guess, kind of like in the first version, we started with a guess and went away from the gradient of the badness function. Here you start with a guess and you just apply phi y to it repeatedly, and you're going to get close to a fixed point of that guy. Okay, so I won't do the details because that would be another video, and we'll talk about the details as they apply to the proof of the inverse function theorem later. But that's going to be another really, really useful thing. Now, okay, when is this going to be true? When is phi y going to be a contraction mapping? Remember, phi y was defined by the identity function minus f of x plus a constant. Remember, y here is a constant. So that doesn't matter. It cancels out here. And so we want this guy to be a contraction mapping. We don't want it to have large variation. We want the variation in its outputs to be small compared to the variation in inputs. What that means is we want f to be close to the identity function. Because then, if we subtract it from the identity, we're going to get something that's small. Okay? In general, that's not going to be true, and so you have to use a more complicated version of this. For our case, we are going to be able to show that f is close to the identity. And in fact, what's going to lead to that is going to be the derivative of f, let's say at some fixed point, is we're going to set it up so that that's equal to the identity matrix, the identity linear transformation, and then that's going to mean that f is close to the identity anywhere near x naught. And again, we'll do the details later. Now, you might think, wait a minute, that's really special. The thing that we're then going to need is a way to figure out, say, well, what if df, the derivative matrix, is just invertible? That's really the assumption that's going to come into the inverse function theorem. But that we'll be able to jigger it so that we'll get something in this situation. Then we'll see that f is close to the identity, and then we'll be able to do this and have a contraction mapping. Okay, so that's going to be the key to the trickiest step in our proof of the inverse function theorem. To finish this part, let me just mention a third possible route to solving y equals f of x. Oh, actually, you know what? I prepared an example, so skip that for a sec. Let's look at an example. I am starting this off with a lot of hand waving, but let's be a little more concrete. Let's say we just want to look at the square root function. Okay? We know how to square numbers. We want to square root y. And in an advanced calculus setting, that's a non-trivial thing to even know that that exists. It has to do with deep properties of the real numbers. How does that fit in with this? Well, okay. This graph, what we were just saying is that we want to look at a place where that graph is not super steep, because we don't want this to be too different from the identity function. In fact, it's going to work best when the slope of this guy is about 1, so when x is about a half. Okay, so that means y, if x is about 1, then y is about 1. So it turns out it's probably simplest to look at 0 less than y less than 1, and to be really concrete, let's take y equals 1/2. So we're going to try and figure out a method for basically approximating the square root of 1/2, okay, which is a very useful thing. Alrighty, so what's our phi y of x? That's going to be x minus x squared plus 1/2. What does that look like? Let me sketch it right here if I've got room. It starts out at 1/2, and at 1, these guys cancel, and you get 1/2 as well. Oh, okay. So by symmetry, that means the vertex is in between. It's downward-facing parabola. It's pretty easy to verify that at 1/2, that's at 3/4. Okay, now, I want to find the fixed point of that guy. All right, so that means you intersect it with y equals x. Now notice, it seems to be intersecting at about 0.7, which is about root 1/2, okay, or 1/√2. Well, what is the, let me use a color here. What is the key idea of fixed point iteration? So I said I wasn't going to say much about it, and I'm not going to give you the whole theory behind it, but I'll give you the key picture. Let's say we start out with a guess of 1/2. What we do is we use this y equals x line in a very creative way. In order to, we keep track of where we are by always referring to the y equals x line. We iterate the function. So we take 1/2 and we plug it into the function. We get 3/4 as an output. We want to convert that to an input. The clever way to do that is if you just go horizontally over to y equals x, that's going to have exactly the right x coordinate, the same x coordinate, 3/4. Now we can go vertically to evaluate the function. Okay, that's going to be, it looks a lot closer to that fixed point. And then we go horizontally to turn the y into an x, and it's going so fast, and my scale's pretty small, you can't really see it, but it's kind of this little spirally, square-shaped spiral spiderweb thing. It's called a spiderweb diagram. And what you can see is this guy's converging rather quickly to exactly the fixed point. So that's very cool. So this is really the picture you should have in your head. This is obviously just a one-dimensional picture. This is a function from R to R. It's not going to have all the complexities of like R17 to R17. But this is really the fundamental thing about an effective procedure for solving this kind of equation and getting a good estimation, and where we have good theory, because we really care about having the good theory. But I wanted to emphasize that you're not going to have good theory very often when the practicalities don't actually work. Okay, so speaking of which, the last thing for this part of the video, this part of the series, solving y equals f of x, really the gold standard for that in terms of like theoretically driven, elegant, but numerically powerful methods is Newton's method. Or Newton-Raphson, because Raphson apparently gets credit for it. I've never looked up the history. And really, if you want to look at the careful theory in multiple dimensions, it actually goes back to Kantorovich in the 40s, I think. He actually won a Nobel Prize for economics, apparently. So he was very much an applied guy. So Newton's method is a very, very powerful way of solving these guys. And the thing is, I'm not going to say much. Right now, I might have an addendum because I haven't set up the version of the inverse function theorem proof with this. This is exactly what Hubbard and Hubbard do. So I'll advertise their book. It's a great book. Okay, and I might well eventually get to this, but I haven't prepared it. Alrighty, so that's kind of the setup. So part of the story of this theorem is going to be using any one of these three methods to carefully show that we can solve y equals f of x. So that's the existence part of inverting. And then we need the one-to-one part, and then all the good features we'd like of the inverse function. We'd like g to be continuous and differentiable, and even continuously differentiable. That'll be kind of another part of the story, and I want that to come out of actually trying to do the proof and getting a little stuck and seeing where we're stuck. All right, good place to stop this one.